Good afternoon and welcome to this 12th week of CS 470 Advanced Computer Architecture. Today we are looking at the second lecture of our hardware security part, and we are going to look into something that has been emerging in the last few years in commercial processors, the idea of trusted execution environments. So what are these trusted execution environments? Well, before getting there, we'll go through a couple of sort of big reminders. One part will be to looking at what are the classic elements that we have been employing until recently, and that make up somehow always the infrastructure for confidentiality and integrity in our computing systems, including looking at some of the evolution that they had, let's say, from the beginning of this century. The second part is to go through what I call the universal ingredients of security recipes, the fact that basically there are a few cryptographic techniques that are at the base of almost everything that we do. And then we will move into the real matter. So how do we handle confidentiality and integrity in our computers? Of course, we know very well, I hope you know very well, but the two key ingredients are, on one side, the indirection created by virtual memory, the fact that individual processes speak in virtual addresses, so have their view of the memory map, and they don't control exactly how it is done, but they have that view of the word, and that view is not the actual view, the actual situation of physical memory. There is a translation in between, and this translation is in the hands of the operating system. And so I cannot access basically the page of my neighbor of the other process, because simply I can only emit addresses that belong to my memory space, to my memory map, and there is no way, unless I control the page table, unless I control this translation, that I can emit an arbitrary physical address and therefore read something else. Now, all this works because I cannot control some parts of the system. Like I cannot control the page table, I cannot control, maybe more specifically in the hardware sense, I cannot control the TLB, I cannot write in the TLB whatever translation I want. And this because there are different privilege levels, there are things that not everyone can do. Now, I said many of the most of the things that are on this slide about the processor levels, the privilege levels of the processor. Also, I mentioned something before, but maybe one thing that I didn't mention is something that I hope everyone has relatively clear. But the point is, how do we handle this privilege level? We are in the same processor. How come that I cannot change the privilege level? Well, the key of the not letting me change my own privilege level is the idea of linking jumping to a specific location, so a control flow decision that I cannot affect, together with the change in privilege. Typically, it is in the form of an exception. In fact, it doesn't really have to be an exception, and is maybe not even a real exception or a classic exception in the sense of interrupt, because I mean it's always a philosophical question, maybe what you call a software exception, an instruction that does a software exception, because essentially it becomes de facto a jump, but it is a jump that at the same time changes the privilege. And now this works because the moment you change the privilege, you raise the privilege, I have more possibilities, well, you're actually executing a piece of code that you don't control. It's a very specific, at a very specific location. And if by the same mechanism, recursive mechanism of protection, before arriving there, before I was even given control of the machine, someone had secured that part of memory, I cannot write anything in that part of memory, so there is a piece of code that I don't control. That is the kernel, that is the operating system, that is the hypervisor, we'll say in a few moments. It is a piece of code that can do what it wants, and I have no control. Whereas I can always go from a higher privilege level to a lower privilege level, because that is, of course, doesn't remove, that doesn't create any security issue. And so that is much easier. It is typically an instruction that I can run whenever I want. So there is this mechanism that is fundamental, right, to change the privilege levels, linking control flow to the change of privilege, because we manage through this to create confidentiality and isolation, basically, and make sure that if I jump somewhere, I may make sure that jumping, whatever is somewhere there, is not under my control. So one of the characteristics of these privilege levels is there have been historical many, most processors implement, or at least implemented more than two historically, trying to have different capabilities for the different levels. People call very often them rings of privilege. And typically, whenever you are in one ring, you have all the rights of the rings, call it outside or above. So you can always do the things that are of lower privilege, but you cannot do, of course, the one of higher privilege. In practice, until a few years ago, these have been disappearing. There tended to be rings that were dedicated for device drivers that are almost sort of parts of the operating system that need to do something potentially dangerous to the machine because they need to handle the IOs, but maybe you don't want to give as much power as the operating system. Somehow, this made things more complicated to handle, so practically they disappeared. Today we have essentially, at least at this level, two modes that are the user mode, or the ring 3, and the kernel mode, or the super user mode for the operating system, that is ring 0. Now, this was the situation until people started to discuss the idea of virtual machines. Now, virtual machines are not new at all, right? They have been, at least the idea, and in some forms, they have been around since the 60s. But there was a renewed interest in virtual machines at the beginning of the century, and especially in the idea of full virtualization, of the idea that I take a standard OS, a standard set of applications, and I run them on a virtual machine. That is, this OS believes that is talking to the hardware of a machine, but is actually talking to a piece of software, call it a virtual machine manager, or these days people call it maybe more hypervisor, that is actually pretending to be the piece of hardware and itself speaks with the actual hardware and multiplexes, in some sense, this hardware perhaps on a number of virtual machines that reside on the same hardware. So again, the idea of full virtualization is that the operating system has not been adapted in any way to know that is not on the real hardware, but is on this virtual machine monitor. Now, the reason for this are many, and I'm sure that you're familiar at least with some of them, right? One is the consolidation, is that instead of having 100 machine with 100 power supplies, with 100 independent memories that are all semi-empty, or some of them are empty and some of them are well used, you put everything into a single machine, and somehow there is a sort of economy of scale that kicks in, and you get a lower operating cost, a lower energy. You have the advantage that I think many of you have maybe experienced. I experience it all the time also at EPFL. I want to have a web page, a web server for some purpose, and we just create a virtual, someone creates a virtual machine, puts it on some server that I don't even know where it is, and I have access to this virtual machine. I do whatever I want. I cannot do any damage to anybody. So there is the last point that is on the slide, better isolation, right? Whatever I do, I mess up with the configuration of PHP. Whatever I do is I cannot damage. So even the configuration of the machine itself, of the operating system, doesn't influence anybody anymore. Whereas if I had only simply different processes, well, maybe I couldn't do something that I want to do. But then if I do that, I damage other processes, right? So better isolation. And of course, the advantage that I can move, these machines can be moved, right? Tomorrow, the machine that has my web server here at EPFL is broken. The virtual machine can be moved somewhere else, and maybe to a machine that is absolutely not really compatible, as a completely different processor, still x86, but a completely different model, different amounts of memory, and so on, and nothing will change. So the idea looked extremely appealing business-wise, and again, it is, right? We have, many of us, I think, have experience of that. Now, doing this purely on software, that is, if you say, okay, now I have this machine that has Linux working and has applications that work over Linux, let me invent a virtual machine so that I can run multiple copies of Linux and so on and so forth, is actually very difficult, right? This is what is called software-based virtualization. That is, we are doing it without having any hardware support for that. Somehow you can do it, right? The basic elements that you need are there, because there are TLBs, because there is a virtual memory in direction through the TLB. It all depends on what you put in the TLB, whether it is, how do you control this? Whatever there is a violation, the fact that there are exception and you get control whenever something goes wrong, you get control through an exception, means that somehow you have all the hooks, if you want, in a software sense, of doing whatever you want. One of the things that are clearly the first difficulty, and that connects to what we were discussing about privilege levels, is that if you have only 2 privilege levels, you don't know what to do with them in some sense, right? Because if you decide that now you have the virtual machine monitor, this new super operating system that handles the virtual machines, you say, okay, this is the guy that needs to do everything in my machine. So of course, this is the kernel mode. And all the others, everything above it, should not be able to do everything, right? So if I do the operating systems, I don't want one of the operating system to be able to meddle with another copy of the operating system running over the virtual machine monitor, because otherwise the better isolation that I had at the end of the previous slide goes to the dogs, right? It doesn't exist. Actually, one operating system can meddle completely in the other operating systems. So they have to be in user mode. But if they are user mode, it's not going to work because they are unmodified operating systems, and they believe they can do things in kernel mode. They think or they want to go into kernel mode in some particular cases. So how can I have an operating system be in user mode and do their job? And again, this connects to what I was saying at the beginning of this slide, to the fact that I do have already traps, hooks, call them as you want, through the exceptions, right? The moment I put an operating system in user mode and it decides to do a particular operation that it thinks it can do because it thinks it's in kernel mode, right? It wants to load something in the TLB and it can't because now it is in user mode. What happens? There is an exception. Now, I will be virtual machine monitor, the real boss. The exception comes to me. I can figure out if what it wanted to do, whatever it wanted to put in the TLB is legitimate given my sense of the overall management of the machine. If it is legitimate, I'll do it for the operating system, and I'll give control back and sort of let it believe that it has done what it wanted, but it's actually me that has been doing it on its behalf. Or if it wants to do something that is not really kosher and is trying to meddle in some other operating systems, I'll actually prevent it from happening, and I will therefore screen the rest of the machine from maybe a malicious OS that is trying not to play by the book. So this can be done, and this is the idea. It's called typically trap and emulate. I trap the kernel mode operations that cannot be done by the operating system, and I will do it for them, the operating systems, plural. There are a number of silly, horrible problems about this. For instance, in x86, and it's maybe a particularity of x86, but maybe it happens in other architectures too, there are instructions that are executable both in kernel mode and in user mode, but do slightly different functionality in the two modes. And you can imagine the disaster, right? Because I don't have the hook that we discussed a second ago. The operating system is going to execute a pop-f, that is one of these instructions that changes semantic depending on the mode. It knows, or it thinks that it is in kernel mode, so it thinks that this pop-f is doing a particular functionality, but is actually in user mode because I'm not letting it go into kernel mode, and then the functionality, the semantic is different, and of course something will go wrong, right? Because it's not happening. The instruction is not doing what the kernel expects. For this, the only solution that people found is, and we know it well because we have looked into that, is dynamic binary translation. Is the idea that we rewrite on the fly the code of the operating system, because again, we don't want to modify it, so we take it as it is, but then on the fly we modify, and we don't really do a translation, but we change those aspects of that code that are incompatible with us. For instance, rewriting pop-f in terms of user instructions, user mode instructions that will do the same thing, implement the same functionality that the kernel mode pop-f will do. Or I would call myself in kernel mode, the VMM, to implement the functionality that really needs kernel mode, and I will do if you want, the trap and emulate, but the trap, which doesn't exist for this instruction, is done by rewriting the code and putting a call to the VMM. So you remember that when we were discussing dynamic binary translation, at some point we actually discussed also the fact of dynamic binary translation where the source and the target are the same instruction set for performance purposes. This is very similar to what people were doing at some point, or trying to do, or playing around in research with these ideas of translation, quote, quote, between one instruction set and the same for optimization. But now we do it because we need to slightly change the functionality. Now, for instance, VMware at the end of the millennium in 1999 managed to show a product that was doing this full virtualization, purely software-based. And actually, I hope you know that the person that did this is a professor in the faculty. And so if you pay him a coffee or a beer, probably you can learn a lot of things that happened in those days. Anyway, the idea was extremely interesting to, as I said, to the business, to the world of computing. And so in 2005, 2006, I think it started with AMD, and soon after Intel, added some ISA extensions and some hardware support to have virtualization, full virtualization in hardware. They added, I think they actually added things that were not completely compatible, and maybe they never even became completely compatible. But what they added are fairly standard mechanism, just extending what existed already in the hardware. For instance, they added again a more privilege level, but instead of being privilege levels in between, if you want, the 0 and 3 that we have seen before, they are below. So there is one new privilege level, at least, that is more important than anyone else, with the same mechanism to go into it, to exit from it, and so on. Many processors by this time, since everybody was using already at the turn of the century or turn of the millennium virtual memory with x86, they have the processors, you know that x86 is not a single ISA, but is actually an ISA that has been evolving with time, and new instructions have been added to help in the page navigation. Nothing else than performance issues to instead of going and read these tables with standard hundreds of standard instructions, you have instructions that with a sort of finite state machine go and do many successive accesses in page tables, in the nested page tables, until they resolve the access. So just to help speed up the address translation, and they just extended it to add the fact that there is one level of nesting more, essentially, for these virtual machines, and a few other elements to help in this virtualization business. So what happened initially is simply that there is this new hypervisor that is below the multiple operating systems. The operating system go back, if you want, to the natural situation of being in kernel mode, but now there is a kernel ++ mode, or an hypervisor mode for the others. And with time, more modes came into the picture. The names vary. System management mode, I think it is an Intel name. Now, one thing that is interesting to note at this point is that while ring -1, the hypervisor ring, is essentially sort of conceptually the same thing as a super kernel mode, with the same mechanism, with the same sort of page navigation techniques that are just extended for one level more of page tables and so on. These additional modes are actually start to become more and more, let's say, different. The system management mode is something that has to do to guarantee something even when the hypervisor is compromised, not to speak of the OS, of course. And so you can, through some hardware interrupts, for instance, go and get some functionality from the processor chip still available. It's mostly, as far as I understand it, it's mostly used for power management, thermal management, for handling hardware errors, right? The moment you have something like relatively catastrophic DRAM problems, you cannot trust anymore anything to work, including the operating system and the hypervisor. And so in some of these cases, if you need to do something to clean up state and so on, maybe you get some help from a even a lower level. And the platform security engine is something similar, even more isolated from the real processor, from the real cores, in the sense that it's really an independent piece of hardware that runs software, that can power up and down the processor, is often network connected, has some reservation of the main memory that nobody else can touch but itself. So these, as I said, are quite different from the simply one more privilege level. These are something else in a sense. They are really pieces of dedicated hardware. They are implemented in some cases with finite state machines. They tend to be, in fact, especially the Ring -3 are small processors like once a few years back, I heard, before it was even announced, and I don't know how many people knew it, but I know the designer of the chief architect of ARC International, and he was telling me, oh yes, there is one of our processor in every Intel chip. And you say, what I don't understand, right? And it turns out that this was the case. I did know. I don't know how much it was publicly known, and now it is known. There was an ARC, and then Intel developed their own x86 minimalist processor to use in that situation. AMD uses an ARM processor because they have a very good relation, and they are a licensee of ARM, so they use that. So it just starts to change the business, right? One of the observations that will come back later when we look at the TEs is that the more there are some of these important functionality, only some of this is actually for security. Some are just management issues, but largely the security of these parts is done by obscurity. Nobody knows, or at least nobody is supposed to know, what is in the code of the Quark processor inside the platform security engine. Nobody is supposed to be able to change it, which might be true or might not be true, because of course Intel is able to change it and to update it and to make firmware updates. So how can I be sure that nobody's doing it? Well, nobody's known officially of how to upload the new firmware, what are the encryption mechanism, and so on. So it's exactly what is called security by obscurity, which is considered one of the worst ways to do security. Before we continue and we see why and how more security and more isolation has been provided in newer processors, I want to revisit the very classic elements or ingredients that are used universally for providing security. You probably know all of these. You're very comfortable with all of these, but I just want to mention so that we are on the same page. First of all, there is a symmetric key cryptography, maybe the most standard or well understood form of cryptography. There is a single key, there is a single secret key that is kept secret by everyone, and it is shared only by the two people that need to share the secret, and it is used both for encrypting and decrypting the message. It's typically used for confidentiality because without the key, nobody can read the message. The next very powerful building block is public key cryptography. That is in some sense similar, except that there are two keys. And the most straightforward use of public key cryptography is to use it as another way of doing encryption, where now one of the keys is considered public, so anyone can use the public key of someone to send a message, and this will create a message that is encrypted, that is not readable, but then only the recipient can use their own private key to decrypt the message. Again, the classic purpose of this is confidentiality, and in some sense is almost equivalent to the previous one, with one fairly important disadvantage, that it is typically the algorithms for public key cryptography are way slower than symmetric encryption. But the beauty of public key cryptography is when you swap the keys. Instead of encoding with the public key of the recipient, you encode with the private key of the sender. So you get a message that is again encrypted, but that everybody in principle can decrypt, so is no longer useful for confidentiality. But by using the public key of Alice, of the sender, you can verify that the sender was the only person in possess of the private key. And this is extremely interesting because it opens a number of possibilities related to signature and authentication. Of course, one of the problems that will come back very quickly at some point is that you need to be absolutely sure that when you are using the public key of Alice, of the sender, is actually their public key and not what someone else pretends to be the public key of the sender. That is a way to basically break completely the authentication process. Another important building block are one-way hash functions, where you start from a message and you have this hash function that is able to create a compact representation of the message, or something that depends on the message, a digest or a fingerprint of the message. And the property of this fingerprint is on two things: that there is no way to go back to the message from the fingerprint or from the digest. You cannot guess or fabricate not even another message that would have the same fingerprint. And you have what is called the avalanche effect, that if you make even a small change in the original message, the fingerprint changes completely. There is it's a practically a completely different signature. And so this is extremely useful for verifying integrity. So since someone that will change your message, alter your message, will not be able to do it in a way that the digest doesn't change, the result is that if the digest is correct, is the same that was there at some point, you are reasonably sure that nobody has altered the message. One of the interesting ways of using hashes is to protect a large set of data, like a file, the content of memory. One of the problems with that is that you have to compute the hash on the complete data set to create the digest and know something that you can use for verifying the integrity. The problem is computational. It takes a long time. So every time that someone changes 1 byte in the memory, you would have, in principle, to compute the complete new hash representing this modification that you have done in the data. So one way to handle this are the so-called hash trees or Merkle trees, where you split your data in many blocks. You do an n-ary tree. In this example is a binary tree. And what you do is that you do hashes for all the little pieces, right? Here you have block 1, block 2, block 3, block 4. So you do hashes independently for all the pieces of your data set. And what you do then is that you hash the hashes of the individual data sets. And you do this recursively until you have a root node when you arrive at the root of the tree. And why is that interesting? I think it's fairly easy the intuition is fairly easy. The point is that if something changes only a little bit, so for instance, something changes in B3, there is nothing to be recomputed for any other part of the tree. What you have to do is that you have to recompute the hash of block B3, which is hopefully sufficiently small to do that. Then you have to create the hash of the newly computed hash and all the hashes of all the blocks at the same level that have not changed, so the hash is still valid, and basically just follow the path to the root, recomputing a series of hashes, of which most of them along the root are relatively simple because they have only hashes of hashes, and you only hashed really a data block that is of the size that you decide is appropriate for you. So it's a much more convenient or efficient way to compute hashes for large data sets. One thing that we will not discuss very much, but is important to be aware, are the difficulty of having random number generators. Most of the time when we say random number generators in computer science, we think implicitly of pseudo-random number generators, which are simply algorithms that from a seed produce in a deterministic way a long string of numbers that look random, have some properties of distribution, statistical distribution that is essentially random. But in some sense, there is absolutely, in a strict sense, there is absolutely nothing random about them. They are completely deterministic. It just depends on the seed. And this is usually not good enough for many applications that need cryptography, advanced cryptography, because you really need to start from keys and random numbers that are truly random. And they are usually not very easy to create and to have really good statistics out of those number generators, but they are typically hardware components that are based on some physical phenomena like thermal noise, maybe temperature variations, something, or process variation in your chip, to generate truly random numbers. They are typically extremely slow, so you just cannot call rand a function and get a great number in a few nanoseconds, but you typically take much more time. So one compromise that often is done is that a true random number generator is used as a seed of a pseudo-random number generator. One of the security concerns is that they have been shown to be sensitive to tampering. Of course, it depends on exactly the technology that has been used to create them, but they are a potential backdoor. There may be techniques to reduce the randomness of true random number generators. So you think that they are fantastically random, but then maybe someone in some way can make them still look superficially random, but actually not so random anymore. And this can be exploited to make to attack cryptographic algorithms that depend on them. Another thing that we are not going to discuss very much today, but some of the things that we will see depend from them are physically unclonable functions. Is again something that is very much physical dependent, implementation dependent. They are the way to have a number, or like a serial number for each chip, and there are different ways to do this. Of course, one way, direct way, will be to have fuses. There are ways to produce fuses in silicon devices and write a different number, a serial number that is characteristic of each chip at the moment of manufacturing. It's relatively expensive to do it, although it is commonly done. And it has the disadvantage from some perspective that the manufacturer knows the serial number. So another way is to have a physical component on the chip that produces this specific identifier. That is an identifier that will not change during the lifetime of the chip. So every time that you switch it on and you ask for this value, the value coming back is the same. But it's sort of different. There is maybe no guarantee exactly that is different for every chip, but is uniformly distributed over a large number of possible values, with then a very high, very low likelihood of collisions. They are used in some contexts, but they are something else that is of a security that is sometimes doubted. One more thing that we are going to see used every now and then are nonces. The idea is that the problem are replay attacks. If you do things based on cryptography and you send a challenge and you get a response, and this response is a confirmation that something has happened from the other party, if you do this by sending always the same type of challenge and getting always the same answer, you open yourself to replay attack. Someone could, if there is an eavesdropper that is listening to what is happening on the channel, can capture one of the response, and next time you send a challenge, sends you the response from the previous time, and you say, oh, great, it's the response that I wanted, and you go ahead. So what people say is that this is lacking freshness, is a stale answer. How do you check that the answer is the answer to the real request that you have sent? Is that every time that you send a challenge of some sort, you add a nonce. And what is a nonce is a number that is used only once during the lifetime of the system. So every time that you send a challenge, you put together with the challenge a number, a different number, and so the answer will change in a cryptographically different way, so in a non-predictable way for the eavesdropper, and just resending the previous answer will not make the cut. Nonces can be done in many ways. One simple way that is most often the case, and we'll see an application of this, is the use of simple counters. A last classic idea that is worth mentioning here, because it will be reasonable a reasonable idea in principle to solve many of our isolation problems or confidentiality and privacy problems that we will discuss a little later is the idea of homomorphic encryption. So the setting is that we have the problem that we want to send our data for someone to process and make sure that whoever is processing is not going to steal our data, but is going to do the correct processing and send us back the result. One of the dream solutions of the problem is to imagine that you encrypt your data, you send them over, and the algorithm that is going to be run over these data can be run on the data still encrypted, and the other party will send you back data that are still encrypted. They have never been decrypted. So imagine that I take a number and I encrypt, I take another number and I encrypt it, I send it, someone does the sum of these two numbers, does something else that represents the sum of these two numbers, sends me back something that when I decrypt represents the sum of the original numbers. Again, the party on the other side will not decrypt, doesn't know the key that I used, but the math that is around the problem is such that whatever operations are done from the other party will perform a given function without seeing the data. It is possible to do. There are solutions for some very specific operations, but there are really very small families of computations where this can be made to work, and there is unfortunately no general solution, and the performance overheads are usually crazy. So it's a beautiful dream. Maybe it's a dream that with time people will manage to make it work, but for now I think it's very, very far away from being usable. We now enter in the at the heart of the problem that we need to solve and to handle. So for doing that, we go back to something that I think we already defined maybe very briefly last week, which is the idea of trusted computing base. The trusted computing base, or TCB, is the set of all components in hardware and software, so pieces, operating systems, maybe applications, whatever it is, and hardware, processor, cache, memory, interfaces, and so on, that we suppose that can be trusted in case of an attack. Now, the purpose of all this is to separate very clearly the things that we do not need to defend against because we consider them in some sense friendly, designed properly to defend our secrets. And if they don't do it, is because of bugs or because of conceptual bugs that we forgot to do properly something, from everything else where actually we think we have no defense, and so the defense has to be created, has to be part of our solution, has to be explicitly added to our solution to make sure that there is no information leakage, security problem, and so on and so forth. I want to note what I implicitly said already when I said I suppose to be trustworthy. When we say trusted computing base, it doesn't mean that it is worth the trust. Maybe it doesn't work properly. Maybe there are bugs, actually, and is part of the problem that we will be facing. It's likely that there will be bugs that could be exploited, and so maybe it is not trustworthy. But that's not part of what we are discussing. What we are discussing is what is the part that we assume is correct, assume will not be jeopardizing our systems. So if we go back to the figure that we have seen a few slides before of a system with all these additional rings, -2 and -3, that have been added in the last few years, and if I look from the perspective of one of the applications of the processes that are running on one of these systems, the classic TCB is everything that we have here, which means that, for instance, we assume that I am secure because of the way the system is constructed between one app and another app on the same operating system in the same virtual machine. And similarly, even more, between the same app and another app that runs in a different virtual machine. Similarly, we suppose that, remember when we were discussing the fact that the hypervisor must have a ring that is even more privileged than the one of the operating system, so that the operating system can do everything for itself, but different operating systems cannot interact, and so therefore there is a safety across them. Of course, the hypervisor is also secure with respect to the operating systems that are above it. So they are just, they can do whatever they want with the application, but they cannot compromise the hypervisor, as it is natural with this sort of system of rings of increased power the lower we go in the in this drawing. But for instance, because the application, our first application and the hypervisor are in the same TCB, the application has absolutely no defense and doesn't need to defend, and hopes that everything goes well with the hypervisor. In fact, the hypervisor has a higher level of privilege, so can see everything that the app is doing, and is not, we assume, is not trying to harm the app. Now, one of the problems that come from this consideration of the TCB is that a malicious app that is in principle isolated from me, and so I am secure against confidentiality losses to this application, but this application can go and try to exploit the fact that there are almost certainly bugs somewhere in the hypervisor, in any of these levels, exploit them to gain privilege like those components, and once it has that level of privilege, because they are within my TCB, I suppose them trustworthy, and therefore I don't protect my stuff against them. If the app gets control of them, I lost completely my security. So the problem becomes, the larger is the TCB, the more code, hardware, components of any sort, hardware and software, there are in the TCB, the larger is the surface of attack, the larger is the probability that there is something wrong with it, non-intended wrong, so like bugs, and someone can discover it and exploit it against me. So there is one of the fundamental mottos of security, probably the most simplest, but also the soundest approach to security, is to say the TCB should be as small as possible. Instead of having millions of lines of codes, if I can have only, say, 1,000 line of code that correspond to my trusted computing base, I have more chances to be secure, because I can read all these 1,000 lines, I can reason about 1,000 lines, I may be able to do formal verification of these 1,000 lines, and gain more and more confidence that it works. When I have a complete operating system written by hundreds or thousands of different people, I can trust the fact that open source means that a lot of people have checked and so on and so forth. But in the end, I'm not even sure what I'm exactly compiling when I'm compiling the kernel, right? I don't know, right? And this is one of the things that are most probably worrying in terms of security, and that people are trying to solve partially looking at hardware solution. Now, this push to excludes parts of the classic TCB from the TCB itself and just make not consider some parts of the system to be trusted and push them out is actually also happening not just to reduce in absolute terms simply the TCB size, but also because very specifically there may be business models that are becoming prominent that create a completely different view of what is trusted and what is not trusted. For instance, the fact that we use more and more the cloud and operators in the cloud to do operations may mean that suppose I am a bank, I am UBS, and I decide that tomorrow I don't want to have any more my own data center, which I think UBS still has, but I rely on some public data center. And so now I am going and I'm going to start an operating system and all my applications on, say, Amazon, on the Amazon cloud. Now the Amazon cloud is running somewhere that I don't know where it is, and I don't know exactly what is the hardware. I cannot guard the hardware. I cannot protect the hardware. So whatever is running there, I don't consider trusted anymore, or I am sure it's not trustworthy because the hypervisor is an hypervisor that I don't know the code. I haven't seen what is running. Because the hardware is not under my physical control, so there may be someone that is tapping the memory bus and is trying to steal secrets by seeing what I'm writing in memory. So there may be a lot of attacks that are possible because of the physical distance that I have from the system, and therefore there are a number of layers and parts that become not part of the TCB anymore. Again, not simply because I want to reduce the TCB for safety, but also because these parts of the original TCB are actually not under my control anymore, and therefore, by definition, not trustable. If we zoom in, and I just sort of mention this in passing, if I zoom in and I look at the more physical structure of the hardware of the computer, there may be things that I can trust. For instance, I can trust the fact that the processor that they are using in this Amazon cloud is a genuine Intel processor, as if I go and look at the CPU ID, it tells me to be. So it is what it tells me to be, and I can trust it to be such. But then there may be other things that I don't trust. For instance, the fact that memory is protected because maybe the bus, the bus is always available in the system. So someone may be putting an oscilloscope or a logic analyzer on the lines between the processor and memory and can see what I'm sending to memory, what I'm sending to the different I/O devices, to the network card, and so on and so forth. So one thing that is emerging is this notion of trusting the processor chip. Why is that? I think the idea is that there is no security in a binary sense, zero security, infinite security, or perfect security. Security is just a question of how much effort, how much money, if you want, an attacker needs to put into breaking a system. And so how much money does an attacker need to put to snoop on my memory, on my memory bus, on my bus to the DDR4? Not that much, a few thousand francs, probably for having a good logic analyzer, and maybe a few man-month to understand exactly the specification of DDR4 and understanding in a proper way from the trace what exactly I'm writing in the DDR4. So it's extremely easy. On the other hand, how easy is for someone that want to make an attack to produce a processor chip that looks in every possible way like a specific model of Intel processor, but is actually not and is malicious in some way? Well, it's extremely more expensive, right? There is on one side the cost of manufacturing a VLSI processor that is huge, right? Hundreds of millions probably. And also the competence, the ability to find people that are able to reproduce the functionality of a genuine Intel processor. On top of that, to the point that nobody notices the difference. So it may be even almost impossible, but it's not a theoretical impossibility, right? It's just extremely, so incredibly difficult and so incredibly costly that I may assume nobody's gonna do. And we will see that this is a leitmotif of whatever we'll do today is basically the idea that, okay, whatever is on the core, whatever is on the processor or on the chiplets that make the processor, is trustable, is part of my TCB, I can trust. And in this spirit of whatever is on the processor is safe, is trusted, processor manufacturers have been trying to leverage from some research projects the idea of building through additional hardware and additional capabilities of the processor compound, of the processor chip, creating trusted, what they call trusted execution environments. That is, areas where only protected software resides and executed, and which are highly separated, highly isolated from anything else, creating therefore a very minimal TCB. And these are the two figures that we have seen a couple of slides before, but actually correspond to the on the left to the AMD interpretation of this idea of trusted execution environments, and on the right to the software guarded extension by Intel. We will look a little bit more in detail to the Intel version, which is a bit more, in a sense, dramatic, as you can imagine also from the picture, because whereas the AMD considers parts of the TCB my operating system, my guest operating systems, and my processes plus part of the hardware, Intel goes one step forward by saying, okay, there is part of the processor, again, the on-processor, on-chip hardware of the processor is supposed to be trusted, and then not even the operating system, nothing is considered to be secure except some little spaces that I create where only the very small part of critical software, like my encryption, decryption, or my most critical processing goes. And these parts, so there are fractions of my applications, right? They are services inside larger processes. These parts are called in, I think it's the language of Intel primarily, enclaves. Now, what is the challenge of doing these trusted execution environments? I guess we have seen a little bit of this problem, or at least the inspiration for where the problem can come from what we have seen last week. The problem is, where is the state that corresponds to my process? So here we go back to the image. We switch between the architectural or abstract view of the processes over operating system and hypervisors, and we go into a more physical picture, and we have this core that is the one that somehow is running this trusted execution environment, right? So it's operating my registers of my processor, contain the values that I need, and the functional units are performing the execution of the TEE, of this trusted execution environment. So everything is here, but the problem is that where is the state of corresponding to my computation? And the state is all over the place. Of course, I have my data that are in memory. Of course, I have my I/O devices that in one way or another are probably participating. I have disks connected. I have network connected. I have part of the maybe uncore of the processor that has been configured in some way related to what I'm doing, maybe DMA configurations or something like this. This is part of this is state, is my data that are known to the programmer, and that's maybe all over the place, but at least I should know. Whether I do know and I can tell is a different thing. But then on top of that, there is all the microarchitectural stuff. And this is exactly what comes back from what we have seen last week, is that I have part of my data that are also on the cache or caches, all the level of caches. I may have some configuration or metadata somewhere in the I/O devices, buffers all over the place that are not necessarily known to me, but they are internal to some of the devices. And these are going to create difficulties for me to create isolation, to create these trusted execution environments that are really isolated from anything else. So how can we handle the challenge of this state dispersed across my system? One of the things, for instance, that is almost automatically needed is that we need to defend confidentiality through encryption. As soon as the data go out of the processor, again, the idea is that the processor complex is safe. So while I am inside there and I'm having my data in the cache, from the perspective of the isolation is not a problem. But when these data are going to be written back in memory, I need to go through a form of encryption that can make sure that whatever I write in memory doesn't reveal any secret. So the typical thing that I will do is to use a symmetric key in this case, because I can encrypt and decrypt with the same key. I have the key. It's somewhere in the core. I need to keep it in the core as close to me. I'm not going to save it in memory or do something like this. So I need some space to keep this key internally, and can be a random key because it doesn't matter what it is, right? And it was one of the reasons when I need a true random number generator to have this key, that every time that I switch on, I get a perfectly random key that I can use for this. this form of confidentiality protection is important against attacks that would be able to, for instance, snoop on my memory bus and see what I'm writing, or cold boot attacks that will go and read my memory after I executed. Normally, confidentiality, or the other big way to handle confidentiality, is through isolation, and isolation means automatically through memory management, the usual way of not giving others access to the memory that belongs to me, because they don't have authorizations, except for the fact that if I don't trust the operating system, if I don't trust the hypervisor, suddenly well, they can everything in terms of page management. They are the ones in control of the page tables. They are the ones in control of the TLB. So if they can do everything on my TLB, my isolation, my classic method of isolation, is gone. Right? It's there is no way to enforce it. And so somehow I need to bring in the page management inside this TE, inside this enclave, inside this protected zone around my core and about my software, somehow in the hardware, and not anymore in the software, in the operating system. And we will see this again in action when we look at Intel SGX, because they will do something of this sort to bring this page management from inside the TE, and not delegated as usual to operating systems and hypervisors. Now, one thing that I already mentioned is this problem of the microarchitectural state. There is not only state, architecturally visible state, but there is also microarchitectural state. I may be leaving traces that are readable all over the place in the system. So one way to handle this is state flushing, making sure that whenever I pass the machine, the control of the machine, to someone else, a new thread in my core, I flush everything that is there. It's something that briefly we discussed last week when we were talking of side channel attacks, microarchitectural side channel attacks. The challenge is to understand what are all the places where there is a confidential state that I need to flush. It's trivial when we say the cache, because we have understood that the cache has microarchitectural state that can be very that makes us very fragile to isolation, to lose confidentiality. But what else? There is microarchitectural state all over the place, right? Any register that I have in the CPU complex, in the processor chip, is, if it is not architectural state, is microarchitectural state. What can be used? Well, it only depends on what people can invent as an attack, and therefore it makes it extremely difficult to identify all the things that I need to flush. On top of that, flushing may not work very well or be very clear in some cases. For instance, if I have this core that is part of my TE, of my enclave, but this core that is not part of my enclave and is doing something else, as you know perfectly well, you can do cache attacks. And now I cannot flush, right? I am running, so I cannot. It's not like I'm flushing before someone else runs. We are running at the same time, so I need to do other things. And in fact, we'll see that today TEs, these enclaves, don't protect against this kind of side channel attacks, because it's virtually impossible to do as a general finding general solutions for this problem. Finally, there is the problem, all these are problems of confidentiality, but then there is a problem of integrity. I put my stuff in memory, maybe I put my stuff in memory encrypted, but what if someone goes there and changes it so that when I read something else? Even if it is encrypted, it doesn't really solve the problem, right? Because maybe people don't know how to change deterministically my content, but already can get me to read something else that I decrypt and comes out with something else. It creates faults, and there are ways of attacking software based on faults, based on the fact of that you can create faults. So it can be very, very damaging. And what is the solution? The solution is probably something connected to the one-way hashing that we were seeing a few slides before, and it has to be configured, has to be sort of used essentially in the same way as the encryption. Not only I need to encrypt, but I need on top of that to hash the content of memory, and I need to store somewhere these hashes. We'll see some of the practical implications of this, but essentially I need to have my counters for the nonces and at least the root, the hash of everything, the total hash that needs to be stored again inside in special hardware, like the keys that we have said before. So many of these things push inside the hardware of the processor because we now assume that the hardware of the processor is trustable, cannot be changed. So we push in there a number of elements, critical elements, in such a way that they are not attackable anymore. It's now time to look into one of the incarnation of these TEs, the Intel SGX, the extension to the ISA of x86 of Intel. And the problem that SGX is meant to solve is exactly what we discussed before, of running some critical software on a remote computer that is owned, maintained by an untrusted party. So I don't trust anything that is in that party except for the CPU chip. The CPU chip is done by Intel. I believe into Intel. We'll see this in a minute again. But anything that is around it, all the hardware that is around it, all the hypervisors, even the OS that maybe I'm using on this remote computer, are not to be trusted. And it's the system, this Intel's SGX, is going to supply me two fundamental properties. One is, of course, isolation, the fact that whatever I do in this TE, in this enclave, is isolated by anything else, by any other software that is running in the machine, and some form of attestation that proves that what I'm running on this machine in this protected environment is indeed what I meant to run there, is my genuine software that I wanted to run there, and has not been modified in any possible way by a malicious operating system or by any other mean. The way SGX works, and we'll see more precisely the details in a few slides, but at the high level is that I do assume that on a remote computer, call it Amazon, I am able to trust only one part of this infrastructure, which is the hardware, to be genuine and to be what the manufacturers has constructed, that is Intel. And although all the software that is there I don't trust, I can set up a secure container. This container is perfectly isolated from the rest of the computer, and I can run there securely, I'm the data owner and I'm remote. Uh, I can send my private data to this container. The container can compute in a way that is not observable by anything that is on that machine, any other process or hypervisor or whatsoever that is in that machine, and I can receive the results back. So I trust my software, of course. I trust Intel, which we'll see is one of the critical elements in this construction. The only thing that I don't, the only entity that I don't trust is the infrastructure owner. I think that anything around the processor of Intel may have been tampered, may have been modified against me, and any part of software that is not my secure container that I set up may have been compromised in every possible way. So if we want to look at a little bit how the sort of the life of an enclave, how does that work, this is my remote machine, and this is my software running above the untrusted OS on untrusted hypervisor whatsoever. So this is, if you want, is my virtual machine that I'm using, and I launch my own process, for instance, that corresponds to an application that is completely untrusted because it runs into an environment that has nothing to make it trusted. What I have in the app that I have uploaded is somewhere some code that is the critical code that I want to execute in the enclave. And typically it will be in an encrypted form so that nobody knows what kind of computation I am going to do, for instance. And what I do in this untrusted application is that I use some primitives, some new instructions in practice of the processor, and that's how I depend from Intel to have implemented correctly these instructions. These instructions set up a secure enclave and copy part of the memory of my application inside the secure enclave. Note that at this point, again, I sort of mentioned it already, right? But anything that I'm doing is non-protected because I'm in an untrusted app. So everybody has seen, I assume, what I am doing and what is my payload. And that's why I decided to crypt it. Now, what I ask, again, through some instructions of my processor, so something that I think I can trust, what I ask to do is to do some hash of what is in the secure enclave. Essentially, I close the secure enclave. Now nothing can be changed anymore. I cannot load directly any more data into the enclave. So I close it and I make a hash and I compute a digest of what is at this point into the enclave. Very important is that all this SGX, all this machinery that is in SGX includes the possibility of doing a classic software attestation process, which is a way to check from remotely what is this hash and be sure that this hash comes from the machine that I wanted, corresponds to the hash that has been really computed inside the enclave, and so on and so forth. Why? What is this attestation good for? Is that if I can read this and have confidence in this hash, I can tell that what is in the enclave is exactly the code that I wanted. And once the attestation has gone through and I am happy with that, what I can do is to launch from my app, from my local app, I can launch some software in the enclave that typically would decrypt the rest of the payload and would create a real sort of is finally I have something like the binary of my secure application that is completely visible in the enclave. And now I can go and run and use it, right? I can, for instance, ask the secure enclave to execute something. Some of the code that I may have typically will be something that through the network gets data into the enclave in encrypted form, decrypts it, does all the computation that need to be done, re-encrypt it, sends it back through the network to my remote location so that I get the results that I want. How do I start executing code in the enclave is something that is somehow similar conceptually to what we know and we discussed before. It's like a high privilege that the enclave has to do. When you are in the enclave, everything can be seen about the enclave, but nobody else can see what is in the enclave. So it is, again, the same mechanism of privilege that is built, and I enter the enclave with the same mechanism of exceptions and so on, but it's orthogonal to the classic levels of privilege. The hypervisor has the highest level of privilege, but has no privilege of executing enclave code that I created, whereas I have the possibility of executing the enclave code that I created and managing. We'll see some of the aspects of memory allocation and managing inside the enclave that typically will be the hypervisor or the operating system that should be doing for me. Now I can do it myself. In fact, I still depend a little bit on the hypervisor to do the right thing, but the hypervisor doesn't necessarily understand what it's doing. I can do that, but I cannot do anything of those things in terms of page management with respect to other apps in the system and so on. So again, I have a very high level of privilege, but only for my staff, whereas the hypervisor has a high level of privilege for everything except for my staff, right? So there is this, in some sense, orthogonal levels of privilege that are new. The conceptual elements are not new, are the usual building blocks that we discussed at the very beginning, but put in a way that is sort of quite different from before. One of the problems that are the classic problems that will also go back a little bit later are, of course, exceptions, right? And when there is an exception, what happens? The classic view of the world is that, of course, it's the operating system that is going to get the exception, right? So if I am in the enclave and there is an exception, well, now the operating system comes into the picture. But that is something that we don't want, because that is a way for the operating system to know exactly my secrets, because it sees all my register, sees all my architectural state. So this should be prevented. And how is it prevented? Essentially by having, if I'm executing code that is inside an enclave, if there is an exception, there is first a handler that is inside SGX, that is this system to handle the enclave, that will remove visibility from the architectural state and will then let the operating system take control as usual, but without having any view of what I was exactly doing. This is all based on a separation of the physical memory in different parts, in the isolation of one part of the dynamic RAM that is done at the moment of boot of the program. So it's the BIOS that is going to decide a part of the DRAM, a part that is as big as you want, but is a power of 2, which is removed completely from the general usage for the processor. And out of this, the kernel or the hypervisor are asked to allocate areas for SGX to use. So this part that is set aside is still somehow provided by the kernel and hypervisor, so that the kernel and hypervisor understand the address translations that need to be done to access this part. But then all the management of this part, that is called enclave page cache, is essentially the memory that is available to the enclave, is completely managed by SGX, again by instructions, new instructions that are inside the processor. And the APC is organized like the rest of memory somehow in 4 kilobyte pages, in standard sized pages. And all these are parts of the standard DRAM, the standard normal memory of our system. And then there is one more data structure that is called enclave page cache map, which is a set of entries that correspond to each of the pages in the EPC and are essentially the metadata for these pages, a bit like the kind of information that you would have in a page table for these pages, that is now handled in hardware, in a sense. We'll see. It's not really hardware, maybe, but in the processor through instruction extensions. And this data that corresponds to maybe saying if a page is being used or not, what type of page it is. We'll see a few examples of which kind of pages may exist, which is the enclave that owns this part of memory. All these informations that are, of course, extremely critical to security and isolation are inside the chip. So they are manipulated exclusively by SGX through these special instructions, and they are inside the chip, so nobody can directly, at least, tamper with that content. So what happens, how the isolation works? Everything is left as usual to operating systems and hypervisor to do all the translations between the virtual address to physical addresses using the traditional means. But once we have the physical address that is ready to go out to the memory chip, what happens, for instance, in case of enclave access, so if it is the enclave that is trying to do the access, is that there are a couple of checks whether the address lands into this APC, in this page cache, and whether the checking inside this metadata is successful. So you can translate this checking the address in EPC as checking whether the address in the page table, that is that a page that you have the right to access, or that it belongs to the memory that has been assigned to you, and check the EPCM, checking the metadata of a page table, that is, can you read it, can you write it, is it really yours, are you the owner, is someone else the owner, despite the fact that is mapped into your addressing space, and something like this. So essentially there is absolutely nothing new, right? There is just one more level of, it's actually not a level of translation, but is a level of checks for the the legitimacy of the access, right? So the translation is left completely to the hypervisor and operating system, so that we don't complexify their life particularly. So they still help us in the allocation and in the translation, but the checks for access are done in exactly the same way, in one step more, and the peculiarity is that this step is essentially what the operating system will do, but now we do it through instructions. It means that what was pure software becomes maybe not pure, but hardware. And why am I saying not pure hardware is because there are functions that are so complex that clearly they are not implemented as is not a RISC instruction, right? A very simple instruction that goes through the pipeline and so on, but is actually firmware, is a set of micro instruction of the x86 that is generated every time that there is one of these x86 new extension instructions that arrives in. So it has achieved the smallest TCB because it has distilled some of the function of the critical functions for isolation of the operating system or of the hypervisor into these few new additional instructions, has put the code that corresponds to it inside the processor due to this assumption that nobody can tamper, nobody can produce a different processor that looks like this and has malicious versions of these instructions. But there are two problems with this, right? One is that is by obscurity. I cannot see what it is, and maybe there are bugs that I will never know. Maybe there are backdoors for some government that I will never know of. So I cannot really look at that. And the second is that maybe the fact that I consider a processor something that is virtually impossible to render malicious, to tamper with, because it's a piece of silicon, is probably a wrong assumption or a too generous assumption, because these are instructions, but they are in some form of firmware that Intel can change, because they do modifications and they correct bugs and problems every now and then, including security issues that are discovered by researchers. But if they can change the firmware, at some point, maybe someone else can also change the firmware. And again, how do you change the firmware? By some cryptographic mechanism, certainly, but that are covered by obscurity by Intel, so we don't even understand exactly how safe they are. So just to give you a sense of the pages that are in this EPC, there are, of course, the main content of these pages for an enclave are data pages, data or code pages, basically. Any page like the operating system gives me normally, that are now given to me by the SGX when I need. So regular pages, but then there are some control structures, right? There is a need to have pages that contain information about what the enclave is, which enclave this belongs to, all the hashes that we have said that are used for attestation. They need to be computed and put somewhere. So there are some control pages for that. There are, for instance, also pages, thread control structure pages, that are used for all the threads, all the processes that are allowed to communicate with a specific, or to run the code that is in a specific enclave. And this brings us to one problem, that is the problem of the exceptions. What happens if I'm executing code that is in regular pages of the EPCs and there is an exception? I was saying it before, right? There is a problem, because if the exception is received, is brought immediately into like it is usual, to the operating system. The operating system has a view, a complete view on our architectural state. So what can we do? Well, the idea is that we have some of these pages, these TCS pages, that are pages where SGX receives the exception. So when there is an exception in the enclave, it's not given to the normal handler, but there is a pre-handler, if you want, that receives the exception, saves all the state, all the registers and so on in this TCS page, because I have to put it somewhere, and the only place that I can have is one of these pages so that I can put it, and then puts in some other state, and then goes to the normal handler, so that the normal handler has no real idea of what was the solution, what was the situation, what was going to, what was happening, as the minimum information to execute whatever needs to be executed in this exception, and then returns to some trampoline, to some indirect place in SGX that is going to restore all the information from the TCS. So again, what is happening here is functions that are absolutely natural of a kernel, right? The kernel, when you have an exception, the kernel, the first thing that it does is dump all the state in some register, so that now we can take care of the exception, and then we take back all the state. All these things are now done in hardware by this SGX extension. Now, on top of all this that we are seeing, of course, it makes sense, all this makes sense only if whatever is in the enclave is completely isolated. And completely isolated means that, for instance, I need to have the memory that is encrypted, and that there is some way to check for the integrity, that nobody manages to tamper with it, right? It's part of the memory map, is part of what goes in the RAM. I have very high, very good isolation internally from the software, because the hypervisor, as we said before, cannot access to my pages, because only enclave code can access my pages. So internally, I have a perfect isolation, but I don't have an isolation from someone that looks into the DRAM or intercepts the information outside of the processor in the board. And so the only thing that I can do is encryption. And the way encryption is done is essentially what you see here, the fact that there is a memory controller that has this memory encryption engine inside, that is, of course, bypassed if we are in one of the general regions, in one of the regions that have nothing to do with the enclaves, but encrypts everything that belongs to the data of an enclave. And we'll see that there is also the problem of the integrity. That means that we have plenty of hashes that we compute, and that they need to be stored somewhere. So there will be some parts of the memory that are used for that. There is not much that needs to be said about the encryption. It works on cache lines. That is the typical and natural resolution for a memory controller to work on. And it is just a hardware encryption and decryption component that uses a key, and the key can be simply generated randomly every session, as we said before, because I just need to do some symmetric encryption and decryption for this session, and I will do something else with a different key next time I'm switched on. Now, one problem that I have is that this area for pages on the belonging to enclaves is limited, is essentially shared by all the enclaves and has a maximum size that is determined by how much the EPCM, that is those metadata that are stored on chip, how much space there is for those. So there is no way to have an EPC that is larger than some very fixed size, and of course, my enclave may need more data, more space, more memory space. Um, Nothing new. What I can do is to swap out. In fact, the name of this EPC contains the word C for cache, right? It's considered that this is only one part of what is in the enclave, but is the part that is alive at a given point in time. So I need to push out sometimes some of these pages. Now, what is the problem with that? While I have a page inside the enclave, it is completely and automatically encrypted, and we'll see in a minute, it is also covered by hashes to make sure that is not tampered with. The moment I am going to put this page outside of the enclave, I have no protections anymore. Now it becomes completely unsecure memory. And different things can happen. There can be tampering. An hypervisor will see the page and will be able to do whatever on it. It's true that it is already encrypted, but maybe there could be replay attacks. Someone can give me an old page and make me believe that it is my page that I just put there, and I take it and I decrypt and I say, okay, this is my page, but is maybe a stale page instead of the one that I just swapped out, and I'm trying to reswap in. So the process becomes a little bit more complicated because the EPC pages is then decrypted with the key that I use for the enclave. And now I encrypt it again, adding some versioning information about one of these nans, one of these counters, so that I can tell that is exactly the version that I'm swapping out now. And I sign it for integrity to make sure that when I get it back, it's still exactly in the same situation as when I'm putting it out. So when I'm going and saving a page outside, I need to save also 128 bytes, and these 128 bytes remain inside the enclave in some dedicated EPC pages for management. So one more type. The good part is that one of these pages will take the metadata of many of the pages that I swap out, so eventually the system will work. And of course, when I need to swap in, I'll do exactly the opposite of what I'm doing. You see also the complexity, right? I have to encrypt, decrypt every time that I am swapping out. Swapping is a costly action anyway, so maybe it's not so catastrophic. Maybe it's interesting to go and look a little bit into how the integrity is guaranteed in the pages that are inside the enclave. This is another set of operations that are done automatically by the memory controller for me. And the way it is done is essentially this mechanism of hash tree that we have seen before, with one particularity, which is that instead of adding to the payload of a page, suppose this D0, U0 being one cache line of data, instead of adding to it a nonce and computing the hash and putting it into the level above in the tree, and then computing from all these hashes and a nonce the hash of the level above, exactly like it was in the slide that I showed before. Here things are a little different in the sense that what is put in the higher level of this hash tree is not the hash, which is what is called here tag, but is the nonce, which is what is called N0 or N1 in this. What is the difference? There is practically no difference, except that now I can do things in parallel, right? Because I don't need the tags at the lower level to compute the tags to check the tags at the higher level. I can do all the levels independently. And there are also some rules that need to be respected to do the write and update. You need to check first all the hashes to make sure that nothing has changed before you start recomputing some of the tags. Anyway, these are all things that are done inside and relatively standard. All these things are done on an actual data structure that is not exactly used. The example that you have here is is a quaternary tree, right? Because there are 4 of these payloads that go into a single hash node and so on and so forth. In this case, only 2 levels. What happens in reality is that things are done in such a way to try to combine at best different pages and packing counters and tags into cache lines in ways that can be very easily manipulated by the hardware. Don't forget that all this maintenance of this hash tree is done by the memory controller, so it's done in hardware. So everything needs to be as efficient as possible to do this well. You have here some maybe interesting information about what happens of my memory. Of course, all these tags that you or nonces, hashes that you are computing need to be stored somewhere, and this means that you have an efficiency of usage of memory. You are using 3/4 of the memory to store your data, but you lose 1/4 of the overall memory available to store these hashes and this information up to the top level of this that has to be inside the processor. Of course, if you leave everything of this in memory, someone that needs to tamper will be tampering and modifying the complete hashes up to the top level, and now you believe that is correct. So you need to have the root of this tree, which is about 3 kilobytes for the complete ERC. EPC, you need to have it stored into internal memory in the processor. And the performance have been measured by, the performance degradation has been measured by some researchers, and depending on the kind of workload, it can be anywhere between 2 and 14%. So it's something relatively okay, right? Just to be clear, in the visual version of what I just said, right? That there is this the memory and the untrusted DRAM that contains protected data and the integrity tree. This integrity tree is around 1/4 of the overall part of the untrusted DRAM that is used for the enclave, and the top level, the root of the integrity tree, is actually not in the DRAM but is in SRAM storage inside the processor. Everything that we have seen depends on a number of keys for encryption, which has to be different for every enclave that is created. Some of these keys can be random, can be ephemeral, in the sense that every time that I boot, I may create another one and I'm happy with it. In some cases, I need keys that are persistent, and I need them to be unique and specific of my processor. In some cases, I need to have a private key of a corresponding, a public key of a corresponding private key that is inside the processor, so that I can tell that it is the processor that is telling me a specific information. The Intel puts two keys inside, two original keys inside each of the processor. They are written in fuses on the chip. One is a key that is stored by Intel. Intel knows it, and this is necessary for giving the public key of that piece of hardware to whoever needs it, and the root sealing key, another key that for other reasons has not Intel promises not to keep any information about this key. And from these two keys, and with different mechanism, all other keys that are needed in the process of running enclaves are generated. But all these creates classic problems that we see in software security, normal security, how to create a public key infrastructure so that I can trust that I have the public key of a specific processor. Is there an authority that certificates that this is the real public key? How do I revoke if something has gone wrong, and so on and so forth? So there is the classic problem of root of trust. How do I really believe in all this? And personally, when I read the functioning of SGX, I have the impression of an extremely complex machinery, and a particularly non-transparent one, because many of the implementation of the different functionalities are completely obscured inside the processor. So it doesn't seem to me a particularly brilliant arrangement. At the same time, it is an implementation of something that seems to respond to a real requirement in the business. To conclude, we'll look now briefly in the ARM Trust Zone, that is the form of TE that is implemented by ARM, and we'll see that is a very different system from Intel SGX, maybe also a much simpler system, partly dependent from the fact that ARM is in a at least the classic market of ARM is a completely different business from the one of Intel. ARM does not build chips, so there is no sense of protecting the actual physical implementation of a chip, like in the case of Intel, because there are no ARM chips. The actual chips are manufactured by others, like Apple, like Samsung, like Qualcomm, and they simply contain ARM processors and maybe implementations of ARM processors that have nothing to do with ARM directly. The idea here is to partition a system and all the resources of the system, also the hardware resources of the system, between a secure and a non-secure world. I think the easiest way to understand this is to think of my cell phone and knowing that I have an operating system that is relatively large and relatively unsecure, like Android. I have a gazillion of applications that come from all over the place, which make all this system particularly non-secure, and therefore having one partition of the system that now is secure, where I can run maybe a very lightweight operating system, secure operating systems, and the libraries that are critical to the security of my and the privacy of my system. So it's essentially about isolation, and about isolation both at the software and the hardware level. At the hardware level, all the communication inside ARM-based systems are typically done by AXI buses, and the idea is to add now one additional bit that informs the system components of the fact that some accesses are not meant for the normal world, but they are meant for the secure world. So all the different components are supposed to react to this and forbid or treat differently accesses that are meant for the secure world. From the software partition, there are essentially these two parts that I said, and there is some monitor, we'll see in a minute, that is used to transition between the two parts. There is only one TE, so it's still a TE, right? It's still a trusted execution environment, but is, as I said, incredibly more simple than the Intel, in the sense that there is only one per system. How does TrustZone handle privilege and isolation in memory? Essentially by adding an additional type of privilege, but is orthogonal to the classic levels. So the classic levels of ARM, I believe, are called thread and handler, but you can read user and kernel, and this is orthogonal, secure, non-secure. So there are really 4 different modes. You can be secure user or non-secure user, and the same for kernel. And if you look at, for instance, register R13, that is the stack pointer that is already banked, that is duplicated so that you have 2 different stack pointers in user mode and in kernel. Now there are 4 copies, so it's really an orthogonal additional partition. And memory is split in 3 parts. A secure memory, a non-secure memory, and then something in between that is secure but callable from non-secure. So it's essentially used as a bridge between or a trampoline, as people say sometimes, between the non-secure and the secure. To call something in the secure world, you have to go through the secure but callable from non-secure, and the API is there is a monitor, there is a number of things in this middle part that handle the exchanges between the 2 parts and make sure that everything, for instance, the secure state, architectural state is clean. Maybe also the caches are flushed so that also the microarchitectural state is clean in between. Now, how do you identify the different memory parts, or how do you protect the different memory parts? It's something that is conceptually similar to what SGX does, but much simpler. There are some units on the path between the physical address and caches and memory controllers, and these additional units just prevent some access to happen in case of violation, and they raise exceptions like it is usual. The simplicity is essentially in the fact that there is a very limited number of secure regions. There can only be 8, so there are only a few registers in these units to check for those regions of very specific size, a conformation, so that the checks are extremely simple to do and not the complexity that we have seen before in SGX. As I said, there are these calling restrictions that from a non-secure, you cannot call a secure library. It forces you to go through this intermediate part where there are some bridging functions that make sure that in both directions, going into the secure and coming back, all the secure state is removed, cleaned, and all the transfers are done in respect of the secure policies. If you look from the hardware view, is what I said before, right? There are components that react correctly to the to this additional bit in essentially the address is like 1 bit more in the address space that indicates whether it is secure or non-secure. Assessing whether a system is secure depends, it needs a very intimate design of the complete implementation of the chip, which is something that depend on the ARM licensee, on the detail of all the components that have been used, on whether these components that are usually very often IP that is supplied by some other party that is neither ARM nor maybe the manufacturer of the chip. So depends on whether this third-party IP is respecting correctly this information about security that is coming from the processor. So it may be relatively difficult to understand from the hardware whether everything is correct or not. The secure word from the software view is a bit more transparent and clear. It's made of a very small, or at least you can make it into a very small TCB, because there must be simply a trusted bootloader, because on hardware reset, the processor starts in secure mode, so you have to set up everything and transition to non-secure mode. You may need to have some small trusted OS, and there are these monitor, these functions to go back and forth from the secure and non-secure world that need to be implemented in the secure world, and for these, ARM supplies reference implementations that are therefore much more transparent than what, for instance, Intel supplies for SGX, that are closed implementations inside the processor. So the security is much less by obscurity. At the same time, system designers in the hardware can probably hide a lot of the security aspects. We arrived to the end. I left this table. It's not that it is very easy to read, but it comes from one of the papers, classic papers that describe this kind of technology and describe specifically SGX, but actually compare SGX with a number of academic and commercial implementations is now a few years old, so some of the information may be a little bit outdated. I think you can have a look to the table yourself. I wanted to notice something that maybe I never noticed today explicitly, the fact that, for instance, SGX is completely unprotected from cache timing attacks. So cache attacks like the ones that we have seen last week and that you'll try to do today in the lab are absolutely still possible. There is nothing that prevents those to happen. What are the conclusions of what we have seen today? What we have seen today is that to try to create this trusted execution environment, there is not a single recipe, and what people mean by these TEs can be fairly different things. From, we have seen one extreme, the enclaves from Intel SGX that are very small ad hoc areas where code can run with a very strong isolation from the rest, to an essentially orthogonal privilege mode as in ARM Trust Zone. Some of these differences depend from completely different threat models and different business models of the processor manufacturers. All these go by a simple and very sound motto that is reduce the attack surface to a bare minimum. So all of them try to put into a corner something that is that needs to be secure and isolate in the best possible way. They do this by what I call glorified version of classic mechanism. There is nothing really original, dramatically original. The mechanism are always the same, are using what we have seen in the first 3-4 slides, using indirections, using hooks through exceptions and something like this. Maybe the only aspect that is really original is having encryption and integrity directly built into the memory system. One of my personal impressions into this is that when I look at the descriptions of things like SGX, I'm terrified by the complexity, and I wonder if the complexity that they implement is not by itself a security threat, in the sense that it's so complicated to understand all the aspects of all the side effects of all these instructions that are added in SGX, that it seems like there must be a problem somewhere. I don't know where. Maybe it's a very superficial observation, but it seems that there are a little too many things. Another observation that I think is important, and this is certainly true, I just mentioned it in the previous slide, but I think it's worth repeating it here. People don't seem to be sufficiently worried yet of some of the side channel attacks, because essentially processors with all these beautiful enclaves and so on are still subject to Spectre-like attacks, or in general cache attacks. I think what we have seen today represents a new aspect of computer architecture that is very quickly evolving and is very recent. Many of these things are within the last definitely decade, maybe even last 5 years, 5-6 years. So they will need time to reach to maturity. So if you compare it with some other topics that we have covered in this course, when we look at things like even simultaneous multi-threading. They are now more than 20, 25 years old. So clearly they have gone through a number of refinement, and they have been distilled in ways that I think it's very clear that this area has not yet gone through and has not reached a similar point of maturity. Thank you very much for your attention, and see you for the next and last lecture on physical side channel attacks.